you separate a pure substance, you get either an element or a compound.
So, you can see physical properties without changing the identity of the matter, but to see chemical properties, you have to change the identity of the matter. Can you say homogeneous? Homogeneous matter is also called a substance, and it has the same chemical and physical properties throughout. Homogeneous mixtures of substances, also called solutions, have the same chemical and physical properties throughout as well. Heterogeneous matter is a mixture of pure substances with different chemical and physical properties. You can separate heterogeneous and homogeneous mixtures into their components by physical means, but pure substances can only be separated into their components by chemical means.
Section B, the elements.
Elements are the building blocks that by themselves or with other elements make up all matter. An element is a substance that contains only one kind of atom. Right now, there are 110 known elements, and each element has its own unique atom that makes it different from the other elements.
So there you are. Close the door quickly. I must show you something very important. A tool that's essential for conquering widespread chemistry ignorance. The periodic table of elements! There are 110 different elements known to man, and you'll find them listed here. The elements fall into three categories: nonmetals, metals, and metalloids. The metals are on the left side and in the middle of the table, with the exception of hydrogen, which is on the left side but is not a metal. The nonmetals are on the right, and the metalloids are in a narrow diagonal strip between the metals and the nonmetals. Neon, argon, krypton, xenon, radon, and helium are called noble gases. That's because we do not combine easily with other elements to form compounds. In fact, neon, argon, and I are never reacted with another element, so they call us inert. I'm so ashamed.
Compounds are made of combinations of elements. A compound is a substance with two or more kinds of atoms combined in fixed proportions.
Dude, so water's a good example of a compound because it forms from the elements hydrogen and oxygen, right?
That's right, and a single unit of a compound is called a molecule. In the case of water, 2 hydrogen atoms and 1 oxygen atom combine through a chemical reaction and form a water molecule. In order for oxygen and hydrogen to come together to form water molecules, a chemical reaction has to make the atoms move from their original combinations to form new combinations. An increase in temperature can increase the rate of a chemical reaction. It's important to remember that during the chemical reaction, the atoms themselves don't change. There aren't suddenly any more or fewer atoms. They simply rearrange themselves to form the new compound.
The molecular formula of a molecule shows the exact number of atoms of each element that makes up a molecule. For water, the molecular formula is H2O. H2 means that there are 2 hydrogen atoms, and O, without any subscripts, means there is only 1 oxygen atom.
So you and everything around you are made up of elements.
A substance consisting of 2 or more elements combined in fixed proportions is a compound.
And the single unit of a compound, a chemical combination of 2 or more atoms, is a molecule.
Part 2. Units of measure.
Like physics and all the sciences, chemistry uses the metric system. You're probably used to the English system, but metric is even simpler, since converting from larger to smaller units, or vice versa, is just a matter of prefixes. We all know that you know the metric system, but here's a quick refresher just in case.
Section A, the metric system and SI units.
This chart shows most of the commonly used prefixes. It also appears on one of your insert cards. You'll see these everywhere, so it's useful to familiarize yourself with them now, particularly nano through mega.
Nano.
Oh, Mark, mega cool.
The International System of Units, also known as SI units, is based on the metric system and has been adopted by most countries. SI units are used for measurements and calculations in chemistry.
These are commonly used SI-based units, and you're going to get to know them all. You'll find this chart, along with the metric system stuff, on your standard Deviants insert card. So refer to it as you hear us use these units of measurement. Meters symbolized by a lowercase m, measure length. Kilograms, abbreviated to kg, measure mass. Seconds, or lowercase s, measure time. We measure volume in liters, symbolized by a capital L, and we measure heat in joules, symbolized by a capital J. Kelvins, symbolized by a capital K, measure temperature. Note that we don't say degrees Kelvin. This temperature measurement doesn't involve degrees, so just say kelvins. We measure large quantities of substances with a special unit called the mole, abbreviated MOL. Kelvins and moles are two important units of measurement, which we'll use constantly.
If you fail to take the proper precautions, these chemistry terms can hurt you. Be prepared. Put out the fires before they start. Learn the metric system and the SI-based units.
Section B, Uncertainty in Measurement.
Okay. All right. When we measure a physical property and we assign it a numerical value to that measurement, the numerical value is always an approximation. See, the accuracy of your measurement depends on the accuracy of your measurement instrument. So no measurement instrument is absolutely reliable.
The terms precision and accuracy are sticky. You may think they mean the same thing, but nope, not in science.
Precision measures the reproducibility of a result. In other words, if we take the same measurement 5 times, will we get the same answer all 5 times? If we do, our results are precise. Accuracy refers to how close our measurement is to the theoretical true value. When I say true value, I mean the value is determined by some brilliant chemist and listed in your textbook. If our measurement matches the theoretical true value, then the measurement is accurate.
When you decide how many digits you want to use to represent a value, you are deciding how many significant figures to use. Significant figures include the numbers on either side of the decimal point that seem reasonably certain. This is a little weird, but they're just some rules you need to learn.
For instance, the number 1.075 has 4 sig figs, and 2.00127 has 6 sig figs. The number 0.0075 has only 2 sig figs, since the zeros in the number only serve to locate the decimal point. Same with 0.0000362. Those zeros don't have value. They just tell you where the decimal point is. So, 0.0000362 only has 3 significant figures.
When you make calculations, you have to decide how many significant figures to use in your answer. If the answer has more figures than are significant, you can round it off. Here are some general rules for sig figs.
For addition and subtraction problems, give the result in as many decimal places as the number in the problem with the fewest decimal places. Remember, decimal places are only the numbers after the decimal point. For example, 10.712 plus 3.61 equals 14.322. But since the number 3.61 in the problem only has 2 decimal places, we can only use 2 decimal places in our answer. The final number just isn't significant.
Multiplication and division problems are handled a little differently. You round off the result so it has the same number of significant figures as the number in the problem with the fewest significant figures. Get the difference? With addition and subtraction, we rounded our answer off to match the number in the problem with the fewest decimal places after the decimal point. Multiplication and division answers are rounded off to match the number in the problem with the fewest significant figures, which can be on either side of the decimal point. For example, 2.32 times 77.96 equals 180.8672. But since 2.32 has only 3 significant figures, our answer can only have 3 significant figures. So we round the answer to 181. Got that? Good. Handle division problems the same way.
And since we're into reducing the numbers of numbers, let's not forget scientific notation. Scientific notation cuts back on the decisions you have to make about significant figures because it reduces the number of zeros in big numbers. You may know scientific notation already, but here's a review.
Scientific notation is a way of writing really big or really small numbers. It uses powers of 10 to express a number. For example, instead of writing 32,100,000,000, you'd write 3.21 times 10 to the 10th power, or 3.21 times 10 billion. It will appear on your calculator as 3.21E10 or 3.2110. A small number like 84 billionths would be written down as 8.4 times 10 to the minus 8th. A calculator would show either 8.4e minus 8 or 8.4 minus 8.
Section C, Dimensional Analysis.
Relax. Although it sounds very complex, dimensional analysis is only a fancy term used to describe the process of converting units.
Here's the deal. We measure dimensions in units like the meters, liters, seconds, and grams we talked about earlier. Chemistry uses lots of different units, and sometimes you need a particular unit to do a calculation. If the unit you need isn't the one you're given in the problem, you have to convert units. You can convert units with the unit factor method. To use the unit factor method, write out the units, kilograms, seconds, meters, or whatever, for every quantity you're using in your calculation. Then carry the units through the calculation, treating them as algebraic quantities. Sounds tricky? It's not. Watch Willie the Wild Worm.
Wild Willie wants to visit his girlfriend Lily, who lives in a compost heap 7.92 miles away. Willie can only wiggle along 1 centimeter at a time. How many centimeters will poor lovesick Willie have to wiggle to cover the 7.92 miles between him and his beloved? Well, we have a problem with this problem. Willie measures his travels in centimeters, but we've measured his travel in miles, so we have to convert to centimeters, Willie's unit of measurement.
Using the unit factor method, multiply the quantity you start with by the appropriate conversion factor until you get the unit you want. In this case, convert miles to feet, feet to inches, and inches to centimeters, since centimeters is the unit you need for your answer. 1 mile equals 5,280 feet, 1 foot equals 12 inches, and 1 inch equals 2.54 centimeters.
To find out how many centimeters Willie has to wiggle, we set the problem up this way. 7.92 miles times 5,280 feet over 1 mile times 12 inches over 1 foot times 2.54 centimeters over 1 inch. The first conversion factor, the one converting miles to feet, looks like this. 5,280 feet over 1 mile. 5,280 feet is equal to 1 mile, so in our equation, multiplying by 5,280 feet over 1 mile is just like multiplying by 1. You know that multiplying anything by 1 doesn't change the value. All we're changing here is the units, so this is when we treat the units like algebraic quantities. Remember crossing stuff out in algebra problems? When we cancel out the miles, feet, and inches in the problem, then multiply it through, we get 1.27 times 10 to the 6th centimeters. It's like we multiplied 7.92 times 1 times 1 times 1, changing only the units, not the values. And hey, don't forget the sig figs. 7.92 only has 3 significant figures, so the numbers in the answer can only have 3 significant figures.
Hey babe, fix me a sandwich, will ya?
So, dimensional analysis is just a fancy way to say unit conversion. Use the unit factor method to convert units of measurement. The unit factor method gets you the unit you want by carrying and canceling units algebraically.
Part 3. Stoichiometry.
Stoichiometry deals with the quantities of stuff in chemical reactions. We use stoichiometry to answer the question, how much?
Section A, Chemical Equations.
A chemical equation is a shorthand way to describe a reaction that gives the formulas for all the reactants and the products. The reactants are what you start with, and the products are what you end up with.
A simple chemical equation is A plus B yields C plus D. A and B are the reactants, and C and D are the products.
Chemical equations have to be consistent with the law of conservation of mass, which says that atoms aren't created or destroyed in chemical reactions.
Atoms are neither created nor destroyed in chemical reactions.
The products of the reaction have to have the same total number of atoms of each element as the reactants had. Remember, the atoms in the reactants have only been rearranged. No atoms have been added or taken away. Pay attention, this is the law.
Order! The jury has decided unanimously that the defendant has indeed violated the law of conservation of mass. Guilty as charged. Guilty as charged. Guilty as charged.
I hereby sentence you to 100 hours of community service, scrubbing graduated cylinders, laboratory sinks, and eye wash stations. Bailiff, wake up and take them away.
Oh, where did I go wrong?
To avoid breaking the law of conservation of mass, you have to learn to balance equations. In chemistry, you will balance equations over and over again. It's one of those things you just have to learn. Lots of the calculations we'll do later depend on information you have to get from a balanced equation. When your chem prof asks you to do these calculations, he or she might give you the balanced equation. But your prof might just give you an unbalanced equation and expect you to balance it. So always look at the equations you're given to make sure they're balanced. If your equation's not balanced, the rest of your calculation will be messed up. So learn to balance those equations. We'll help you. Let's look again at the reaction that forms water.
The chemical equation representing the reaction that goes down between hydrogen and oxygen to form water looks like this. 2H2 plus O2 yields 2H2O.
H2 is a molecule with 2 hydrogen atoms, and O2 is a molecule with 2 oxygen atoms. Each water molecule has 2 hydrogen atoms and 1 oxygen atom. The unbalanced equation representing the formation of water is H2 plus O2 yields H2O. This equation is unbalanced because there are 2 hydrogen atoms and 2 oxygen atoms on the left side, but there are 2 hydrogen atoms and only 1 oxygen atom on the right side. One of the oxygen atoms on the right is gone. The law of conservation of mass says that atoms aren't created or destroyed in chemical reactions, so this equation violates the law.
You see, the key to this balancing equations thing is to keep the proportions of the molecules on each side of the equation. O2 consists of 2 oxygen atoms, so we have to make sure both atoms are present and accounted for in the product on the right side of the equation. To balance the number of oxygen atoms on the left side of the equation with the number of oxygen atoms on the right side of the equation, the first step is to place a 2 in front of the product H2O. Now there are 2 oxygen atoms on the left and 2 oxygen atoms on the right. Hey, you're on your way to a balanced equation.
Alright, now the oxygen atoms are balanced, but we're not done yet. The hydrogen is still not balanced. There are 2 hydrogen atoms on the left side, but now there are 4 hydrogen atoms on the right side.
Right. Now what?
Just throw a 2 in front of the hydrogen molecule on the left side of the equation. This gives us 2 times 2, or 4 hydrogen atoms, and an equation of 2H2 plus O2 yields 2H2O. We are now within the limits of the law of conservation of mass, because all the stuff is being kept in the same proportions. That's the key.
Here's a harder one. This equation is the reaction between iron and oxygen that forms iron oxide, or rust. The equation says that iron and oxygen combine to yield a compound that has 2 iron atoms and 3 oxygen atoms.
So how will my son balance the atoms on the left with the atoms on the right? Help me rehabilitate him.
Well, ma'am, first he has to figure out how to balance the 2 oxygen atoms on the left with the 3 oxygen atoms on the right. Since both 2 and 3 easily multiply to 6, he can try to get 6 oxygen atoms on each side of the equation. If he puts a 3 in front of the O2 on the left and a 2 in front of the Fe2O3 on the right, then each side will have a total of 6 oxygen atoms. So the oxygen is balanced. Next, he has to balance the iron. Since he added a 2 to the right side, he has a total of 4 atoms on the right. 2 iron units that have 2 atoms each. Now, getting 4 iron molecules on the left side of the equation is easy. He can just put a 4 in front of the Fe. Once again, you see the proportions are the same. If your son does this, he'll be abiding by the law of conservation of mass. Now come up here and explain this to me, son.
Well, sir, the 4 iron atoms on the left side of the equation are represented on the right side of the equation by the 2 iron units which have 2 iron atoms each. And the 3 oxygen units on the left side of the equation, which have a total of 6 oxygen atoms between them, they're represented on the right side of the equation by the 2 compounds with the 3 oxygen atoms each. All atoms are accounted for, so it all balances out, sir.
Good work, son. Section B, atomic and molecular weights.
Of all the elements, hydrogen has the smallest mass and the simplest structure. A hydrogen atom consists of 2 electrically charged particles, the proton, which has a positive charge, and the electron, which has a negative charge. As small as it is, the hydrogen atom has measurable mass. 99.9% of the mass of each atom is contained in the nucleus of the atom, where the protons are. Because as small as protons are, an electron's mass is much, much smaller.
Hydrogen is the first and simplest element in the periodic table. The second element, helium, and all other atoms except hydrogen have another type of particle in the nucleus. The other particle is called a neutron because it's neutral, like Switzerland. It has no charge.
I'm the first element on the periodic table with a neutron. My neutron increases my mass, gives me X-ray vision, and lets me fly at supersonic speed!
The neutrons are in the atom's nucleus along with the protons. The nucleus of every atom has an electrical charge which is determined only by its protons, since neutrons don't have a charge. The neutrons definitely count, though, when you consider mass. The mass of the nucleus includes the combined mass of the protons and neutrons. The combined mass of the nucleus and the electrons is the total atomic mass.
Mass number is the total number of protons and neutrons in the nucleus of an atom. The letter A represents mass number. The atomic number is the number of protons alone in the nucleus. Z is the letter that stands for atomic number.
The total number of protons plus neutrons in the nucleus is the mass number, which we'll represent with the letter A. The number of protons alone in the nucleus is the atomic number, which we'll represent with the letter Z.
There's a general notation to represent the mass number and atomic number for any element. Let's say Q represents any element. Write the mass number of Q as a superscript on the left, and the atomic number of Q as a subscript on the left. Here's what the notation looks like for the element helium, which has a mass number of 4 with 2 protons and 2 neutrons in its nucleus, and an atomic number of 2, which stands for its 2 protons.
Number 6. Number 6.
In the periodic table, the elements are arranged in order of increasing atomic number, which usually matches the order of increasing atomic mass.
The periodic table is arranged in periods and groups. It has 18 main vertical columns called groups, and 7 main horizontal rows called periods. This arrangement places elements with similar properties in the same column. The atomic numbers are usually noted above the symbols of the elements. Average atomic masses appear below each symbol. There are two general trends in the periodic table. Going down any group, the atoms get larger. Going from right to left across any period, the atoms get smaller. Down larger, left smaller.
Down larger, left smaller. Down larger, left smaller.
Some atoms of an element have different numbers of neutrons in the nucleus than you're led to expect by the periodic table. Such atoms are called isotopes. Take carbon, for example. On the left is carbon with the mass number 12. Using that nifty notation, we can tell that the carbon atom on the left has 6 protons and 6 neutrons, since the atomic number on the bottom tells us that the carbon has 6 protons, and the mass number on the top tells us it has a total of 12 protons plus neutrons. Subtract the number of protons from the mass number, and you will know how many neutrons are in the atom's nucleus. In this case, there are 6. The carbon isotope on the right also has 6 protons, of course, but since the mass number is 14, we know that there must be 8 neutrons in this atom's nucleus instead of just 6. So carbon-14 is a carbon isotope.
Atomic masses are measured in atomic mass units called AMUs. See, we measure atomic mass with AMUs, so we'll have a standard of reference. Some ancient colleagues of mine decided to make carbon-12 the standard, so they assigned carbon-12 a mass of 12 AMUs. That means that an AMU has a mass equal to 1/12 of a carbon-12 atom. See, measuring the mass of atoms with AMUs keeps the measurement darn close to the mass number, which is A. So all masses measured in AMUs are relative to the mass of carbon-12.
It's like referencing the distance of Chicago, New York, and Los Angeles by their distance from Washington, D.C. Washington, D.C. is the standard reference point, and the other cities are measured from that point.
So carbon-12 is the standard reference point for the mass of atoms, and the masses of all atoms are measured from the standard set by carbon-12.
Warning, beware of hazardous terms. AMUs are sometimes referred to as Daltons. If you see the term Dalton, don't panic. Handle the Dalton the same way you would handle an AMU.
Deciding which college to attend is an important choice in your life. You want one that has it all. Here at Atomic Mass University, we provide the smallest particles in the universe with an expansive education at an affordable price. AMU, founded a nanosecond after the Big Bang, is located just outside the nucleus on a pastoral 10 to the 23rd acre campus. To arrange for a campus tour, please call 1-800-238-9669.
Okay, so you know some elements have several isotopes. Using AMUs, we can calculate the average mass of the isotopes of an element. Why would we do that? Well, because there's a good chance you'll have to do it on a test. Besides, the mass in AMUs listed for each element in the periodic table is actually the average mass of the isotopes of the element. It's the mass of the hypothetical average atom for each element. We'll show you how to figure out the average mass in AMUs as it's listed in the periodic table.
Don't worry though, it's easy. You need to know the atomic mass of each isotope. You can look that up in your textbook. And you need to know a thing called the natural abundance of the isotopes. Natural abundance describes how much there is of a particular isotope in comparison to other isotopes of the same atom. For example, of all the hydrogen in the world, 99.985% of it is the hydrogen isotope with 1 neutron. So 99.985% of it is the natural abundance of the hydrogen isotope with 1 neutron. You can look up the natural abundance of an isotope in your chemistry textbook. Then, a quick calculation gets you the average mass of the isotopes. We'll show you how.
We'll use 2 of hydrogen's isotopes to show you how to calculate average mass. Find average mass by multiplying the natural abundance of each isotope by its atomic mass, then add the contributions of each together. Again, you can find the natural abundance and atomic book. So here we go. The hydrogen isotope with 1 neutron has a natural abundance of 99.985%, and the isotope with 2 neutrons, called deuterium, has a natural abundance of 0.015%. The mass of the first isotope is 1.00783 AMUs, and for deuterium, 2.01410 AMUs. Multiply the mass of each isotope by its natural abundance, then add the two products together. The result is 1.0080 AMUs, the average atomic mass of the hydrogen isotopes.
AMUs and isotopes, balanced equations, and the unit factor method are all the things you'll need to understand later when the calculations and the